We're talking about graph theory. And remember from last time, some basic terminology. A graph is just like a thing like this. It has the dots and the lines. The dots are called vertices and the lines are called edges. Vertices and edges. All right. The degree of a vertex is the number of edges that come out of it. So like on this example right here, this has a degree of 2 because there are 2 edges coming out of that dot, right? This one is also a 2. This one is a 3 because from here I see, I see 3 edges here, right? So this one has a degree of 3. Somebody show me the fingers. So what's the degree of this one? You should be able to show me the fingers. I say 4, right? There are 4 lines coming into that one. So this is a degree 4. This over here is a 1, right? There's only one edge here. So that's a 1, that's a 1, that's a 1. Those are the degrees. In all the like applications of graph theory in real life, degrees are typically important. All right, and then the other word that we talked about is connected, which is a very natural concept. Connected just means that you can always, like from any one point to any other point, you can actually get there inside of the graph. This is the same as saying the graph all kind of comes in one piece rather than being sort of separate into 2 pieces. All right, this is the basics of what a graph is, as we discussed last time. I want to talk about some examples, and I talked about a couple last time about just sort of modeling a real life situation using a graph. So, and these are, you'll have like a few of these on the homework, and there's even a whole item on our big checklist about this. Sort of imagine a graph type problems where I will describe to you some kind of a real life scenario, and then you want to convert that into a graph and then answer some basic questions about that graph. So here is an example. How about, let's say, imagine a graph where I'm going to tell you what are the vertices in this graph, what do they represent, and then what do the edges represent. So imagine a graph where each vertex is a full-time Fairfield University student. All right. So all of you appear as a vertex in this graph, and then like every student at the university. So this is a very big graph. It has, however many students there are at Fairfield University, that many vertices in the graph. And I also have to tell you what the edges are. Each vertex is a full-time Fairfield University student, and 2 vertices have an edge if those, like 2 vertices are 2, students at the university. 2 vertices have an edge if they are in a class together. This semester. All right. If they're in a class together this semester, there's an edge. And if not, there is not an edge. All right, so I hope you all have some idea of what this graph looks like. It's a very big graph because there's, a different vertex for every student. But you all are students at Fairfield University, and so you all have a vertex in this graph. And 2 vertices have an edge if they are in a class together this semester. So let's ask some questions, some basic questions about this. How about what is the typical degree of a vertex? Now, everybody, because of the way this graph is built, everybody's degree is going to be different. It would depend somehow on what other people you are in classes with. But could we say, just as a matter of sort of like a Multiple choice. Is it like, is it like 1 or 10 or 100 or 1,000? Something like that. Between these options, what do you think would be reasonable for the degree of a vertex? You have to imagine, like, you are one of the vertices in this graph. So you could say a little, like, here's me. How many other vertices are you connected to? Anybody think it is? I think it is not 10. Anybody agree? Explain why. I would say actually 10 is too small. Anybody agree? I'm asking basically, like, how many edges do you think there are connecting to you in this graph? It says 2 vertices have an edge if they are in a class together this semester. What do you say?
A lot of people, like, you're going to be in a lot of classes with different people because you take different classes, so it's going to be like more than 10.
Yes. She says, I'm in a lot of classes with a lot of different people. You're in what, like 6 classes? 5 classes? It's definitely not 10. I mean, there's more than 10 people in this class, right? So, like, you're automatically connected with everybody else in this class, but then additionally you're connected with everybody else in all of your other classes. So I would say, I'm sure it's different for different ones of you, but I would say of these options, at least 100 is probably the closest, right? 10 is definitely too small. I think 1,000 is definitely too big. You're not in classes this semester with 1,000 other people, right? So I would say this represents, so the degree here, could I like say in words what the degree is? The degree, that's not how you spell degree. Degree. Is the number, it's really just like for you, it's the total number of people in a class with me this semester, which might be 100. I mean, 100 is probably a little too big for that, but I would say like between 50 and 100 probably. All right. Of those options, 10 is too small because we have more than 10 even in this class by itself, and 1,000 is too big. Like, we don't have giant classes at Fairfield, so you're not in classes this semester with 1,000 other people. All right. These are the kinds of questions that I am going to be looking for on this sort of a thing. How about, could we answer, do you think the graph is connected or not? Is it connected? This again, I suppose because we don't actually know exactly what the graph looks like, it's not possible to be completely sure about this, but I have some idea. Anybody have an idea of whether this graph is connected or not? What that means is, remember, connected means from one vertex to another, there's always a way to get from here to there by connections inside the graph. Is that actually true about this graph? Anybody got a feeling? Anybody else got a feeling? Your feelings are valid, I'm sure. I want to hear someone else's feelings. You have to imagine, if you start from one person in the graph, like say yourself, and then pick out any other person, can you get from you to them inside the graph by following connections? Nobody's saying nothing. Got an idea?
I think it's not connected.
Why do you say that?
Just because, like, because all like the different majors and like there's people in different schools at Fairfield, so it's kind of unlikely. Like, if you are in a class like if you're a freshman, you're in a class with another person in like a business class, it's pretty unlikely that that person shares a class like a senior like nursing major or something.
Yeah, that may be true. It's hard to. I would say the answer to this is it's hard to be sure about this. I was going to say I think it probably is connected, although I think you could go either way. What you're saying is a good read on the situation. What you have to imagine is, say, just take like any random other student at the university. Now, if you choose another student at random, you are probably not in the same class with them, so there's not going to be an edge from you to them. But is it possible that there's a sequence of edges, like I'm in a class with this person, and they're in a class with this person, and this person, eventually arriving at the other person? I would say, I feel like that's probably always possible to do, to connect from you to any one other student. Now, like he said, it is possible that maybe some people are like, I don't know, only in a few very small classes, and those people somehow are not connected to the rest of the group. But I feel like this graph probably is connected. So I'm gonna say, I'll say yes, probably. Why I say that is, given any two students. Now this may not actually be true, what I'm saying here, because of issues like he mentioned, but given any two students, probably you can find connections of the form like, I'm in a class with, whatever, who's in a class with whatever, etc., who's in a class with you, right? Something like that is probably possible. If you meet some fine young fellow at a party this weekend, and you're like, I haven't seen you in any of my classes, he might be like, well, yeah, but like, I'm in a class with this other guy, and that other guy's in a class with this one, and this one, and this one, and this one, and they're in the class with you, right? That would be a very weird interaction to have, but I think probably it is possible to find connections like that in Fairfield University. It may be that for some people, for weird reasons, that couldn't happen, but I think that's probably possible. All right, so I will say, yes, probably it's connected, although, I could believe it if it wasn't. This is, by the way, why I said full-time student. If you include people who are like only taking one class this semester, then it may be that they are just not, they don't have enough connections in order to be connected with anybody else. But I don't want to consider such people. All right, I hope that everybody is able to think along. Nobody's really saying anything. Hopefully that's because you just don't want to say anything, not because you don't know anything. I got two more examples, and then I have one that I would like for you all to think about. How about, again, this is a graph involving Fairfield U students. So this is a graph in which the vertices are Fairfield U students. And I'm going to say this, but the edges are totally different. So it's different types of connections I'm talking about this time. The vertices are Fairfield students, and they are connected by an edge if they come from the same U.S. state. Or, I know there are some international folks at the university, even in our class. Let's say if they come from the same U.S. state or same foreign country. All right? The vertices are Fairfield U students, and they're connected by an edge if they come from the same U.S. state. Let's just assume that everybody sort of has a home state. I know this is probably not true of everybody who, like, some people move around a lot, but let's just assume that everybody sort of comes from a state or some foreign country. And two students are connected by an edge if they come from the same U.S. state. This is the graph, all right? Can you imagine this graph in your mind? Again, it's way too big to draw a picture of this graph, but this is the graph that I am trying to imagine. All right. let's again talk about the degrees. I think the degrees of various people in this graph are actually very different from person to person. For example, a specific question: who has a bigger degree in this graph? Joe from Massachusetts or Sky from California? That sounds like a California name to me. All right. Who has a bigger degree? Joe from Massachusetts or Sky from California? Southern California, I imagine, is where Sky would be from. Maybe Northwest. What do you think?
Probably Massachusetts.
As a California resident yourself, yeah. Why do you say that? I agree. This one has the bigger degree.
Because I feel like there's just more people from the tri-state area who go here, and there's like a lot less people from the West Coast.
Yeah, that's right. Remember, the edges would connect, so like Joe here would be connected to everybody else who is also from Massachusetts. And that's kind of a lot of connections. Like there's a lot of people from Massachusetts here. Whereas Sky from California would be connected to all of the other people from California, but that's not a lot of people because there aren't a lot of people from California. So Joe from Massachusetts has a bigger degree, and that's because he's connected, like by an edge, to everybody from Massachusetts. And there's a lot of people from Massachusetts. And Sky would be connected to everybody else from California, but there's not a lot of people from California. And so the degree of Joe is much bigger. Great. What would you say, is this graph connected? Actually, this one I think we can answer for sure, yes or no. Is it connected? Remember, connected does not mean there's always an edge between two vertices, but it means like from one vertex to another, you can sort of go from here to here to here to here along edges and end up at the other one. Is that always true in this graph? What do you think? No. Why not?
Because you're not going to be connected. If you're from Massachusetts, you're not going to be connected to somebody from like California or Connecticut.
Yeah, right. In this graph, like Joe from Massachusetts is not connected to Sky from California by an edge. And it's not even possible to get from Joe like to somebody else, to somebody else, to somebody else, and end up at Sky from California. That's because if you're starting at Joe, going to somebody, they're all going to be in Massachusetts. You can never get out to Sky. So the answer to this question is no. That's because the graph, I would say, as you're imagining this graph, the way that I imagine this graph, the graph has separate, and there's actually a word, this is the technical word that we use, not that, component. The graph has separate components for each state, right? So there's like one fairly big component, which is all the Massachusetts people, and they are all connected to one another in all possible ways, right? This is like the Massachusetts one. And then there's another one for California, which is much smaller. Maybe there's only like 5 people from California, and they are all up connected, right? This is the smaller one. And then there's one for Connecticut, which would be much bigger. One for New York, which would also be way bigger. All right. So the graph has separate components from each state. You can't connect a vertex from one state to one from another state. So it's disconnected. All right. Great. I hope that's making sense to everybody. So actually, I would say like these two graphs that we've talked about so far are actually very different. Like this one, if you could see the graph like drawn on a piece of paper, it would look like a whole bunch of separated chunks of varying sizes. Whereas this graph here about who's in the same class with who else, this would just be like one huge thing with lots of connections all over the place. Not so for this one. It would be a bunch of separated chunks. All right? They look very different. Okay, I got one more. How about how about a graph in which the vertices are people in this room and an edge. Like, I always have to tell you what are the vertices and what are the edges. The vertices are people in this room and an edge between any two people whose ages are within 6 months of one another. All right, this is the graph I would like to imagine this time. All right, we have probably, I don't know, about, looks like about 20 people in the room right now, 15, 16, 17, 18, between 15 and 20 people in the room right now. An edge connects any two people whose ages are within 6 months of one another. All right, let's talk about things like what's a typical degree going to be like here? You could think about yourself. How many other people do you think you are connected to in this graph? And it says you're connected to anybody else whose age is within 6 months of yours. Would you believe me if I said, I mean, it's not hard to say because obviously we don't know exactly how old everybody else is here, but would it be something like 1 or 10 or 30? I think one of these is much more reasonable than the other two. What do you think? I think probably for most of you, 10 would be a reasonable thing. That would mean there are 10 other people in this room that you are within 6 months of in age. I think that's probably true, right? I think 1 is too small unless you know something that I don't about your age. Actually, there's one person in this room whose degree is 0. I think none of you are within 6 months of my age. I count. I'm in this room, right? I'm a person. So my degree is 0 because there is no edge from me to any of you because you're all younger than me. I can only assume. But all of you have probably many connections with each other. I don't really know how old you are. Maybe one of you is much older or much younger than everybody else, but probably not. So I would say a typical degree here is something like 10, right? It could be that you're all within 6 months of each other, and then your degree would be 15 or whatever, like how many other people there are here. So a typical degree, I would say, is about 10. 30 is way too big. There's not even 30 people in the room, so it's definitely not possible that your degree could be 30. I suppose in theory your degree could be 1 if you're the oldest person in the room or something like that. You might only be connected to one person. I think that's probably unlikely though. All right, I would say 10 is a typical degree here. My degree, prof's degree, I already said it, is 0, right? That's because no other person in the room is within 6 months of my age, I don't think. What would you say about this graph? Is it connected or not? What do you think? Again, we can't be completely sure about this, but we can guess.
Does it include you still or no?
Tell me either way.
Well, we can't extend it to you because you're not within 6 months, so it's disconnected.
Yeah, right. So if you consider me as part of this graph, it's disconnected because like none of you can get to me by an edge through other people which are within 6 months every time. But I think without me, it would be connected. I would assume that all of you could be connected up with one another. Maybe not directly by an edge, but probably through some other people. So I would say it is, well, I would say not connected since me, the professor, is sadly all alone. But the rest is probably connected. So if I were to draw this graph, I mean, we could, by actually figuring out how old everybody is, you could draw this graph out. It wouldn't be so big. It would have, a bunch of edges connected in some way with each other over here. This is all of you guys. I don't know exactly how they would be connected. And then there's me over here, right? This is what the graph looks like if you were able to draw it out on paper. It has all of you in one connected component is what we call it, and then me in my own component all alone. All right. This is me. You are in the other batch somewhere. All right, great. I would like for you all to try a similar thing. I don't do this a lot, but I want you to chat with somebody near you. If there's nobody near you, you can turn yourself around or something like that. I would like for you to come up with an example. Just invent another example. It could be about people, but it could be about anything you like. It could be about, animals in the animal kingdom or something like that. So I would like, take a moment, chat with your neighbor, invent an example of your own. Your example must consist of the vertices are, you say something, and you also have to tell me 2 vertices have an edge when something. And then I would like you to also think about, in your example, what are the degrees like? Now you probably won't be able to be very specific, but is the degree of each thing like 5 or 500 or something like that? So what maybe specifically you could say, what do the degrees represent? Like in our examples, in the one we just talked about, the degree would represent how many other people there are with age within 6 months of you, right? That kind of a thing. And then if you can, is it connected? Yes or no? Or you might say, I don't really know because it's complicated. All right? This is what I would like you to chat with your friends about. I'm going to walk around and see how you are chatting. Thank you for talking with one another. I appreciate
For
it.
mine, I did, the vertices are Fairfield U students. I said that the edges are connected when they live in the same dorm. And the degree is probably like 200, 300, however many people live in each dorm, and it's not connected. Because, they just like if somebody lived in 2 different dorms, there's no way that they'd be connected to each other. Yeah.
All right, great.
Travel to the same U.S.
There is an edge. Those 2 people have been in the same city forever. Okay. This is kind of interesting. Or maybe sort of I don't know. Think about the
Okay.
Perfect.
Yeah.
There's gonna be lots of
You guys got the ideas?
Yeah, we're doing dogs.
Dogs, okay.
We're doing like parts on the classroom of a dog, and then the edges are connected to like edge and
I know, so you guys can scan it.
Yes, can.
Yeah.
Like, do you have people that don't?
Because we got this.
So, how do I tell if there's an edge or not between you?
because we have a dog.
I feel like some people who like, I live here.
Or maybe do one if like
You have to say something like, if your dog and your dogs, like there has to be a way of saying.
Both golden retrievers.
I don't know if that's like enough to make it.
Yeah.
Or like both like both
It could be
within
like-
the age range of like 6 and documented.
Yeah, I would say, these are all fine. It maybe it's more interesting if you don't use the word both. Like, if your dogs, you know, if your dog likes your dog, then they're between those two dogs. You have to think, yeah, something like, you just have to think about, here's a dog and here's another dog. When should they be connected?
Yeah,
Yeah,
like,
you use those things that you can say.
I just really want to connect in their
Sure,
reverse.
yeah.
So if we did say like they had like, yeah, like brown eyes.
Well,
Probably has brown eyes.
but you should say something more like, if this dog and this dog have the same color eyes or something. Because if you say, like, if you say, if it has brown eyes, then it's one dog. But I want to be thinking about two different dogs and decide what determines if they're connected or not.
I'm sure.
Yeah. You got any ideas here?
Yeah, I said vertices are Fairfield students living on campus, and then they share an edge if they live in the same dorm.
Okay, yeah, sure, great. All right, I've heard some great ideas. Thank you for talking with one another. I don't know if you've noticed, I'm not big on like making people talk during class, although I think it is helpful sometimes. I do like to like respect people's right to just sit there quietly. Maybe this is just the kind of person I am. If I'm somewhere, I usually like to sit there quietly, and it annoys me when people want to make me. I think like the worst thing is like when somebody addresses a group of people and they're like, hello, good morning, and they all say, good morning, and he's like, come on, guys, you can do better than that. Good morning. I hate that. I want to like, I have a right to be unenthusiastic when you walk into a room. So anyway, all that to say, I appreciate you talking. I don't like making people talk to each other, but sometimes it's called for. I heard lots of great examples here. Maybe I would just give a few. Somebody said there was a lot of people who went with all Fairfield students or something like that, but here was a good one. All Fairfield students are the vertices, and the edges were two students are connected by an edge when they live in the same dorm. All right. I think this is a fine example. So that means you are connected by an edge with everybody else in your dorm, but you are not connected by an edge to anybody else who lives in a different dorm, right? Maybe somebody other than the folks who came up with this idea, can somebody tell me, is this connected or not, this graph? Try to imagine what it looks like. Is it connected or not? Any thoughts? Maybe could I hear from someone in the back row? They're all avoiding eye contact. Is it connected or not? You're in the back row, all right. I was looking at them.
Would it not be because like if I live in Gonzaga and my other friend lives in Campion, like we're not connected?
Yeah, right. If I live in Gonzaga and someone else lives in Campion, like I could only be connected to the other people in Gonzaga. And even if you go like I'm connected to him and he's connected to him and him, it still is never going to leave Gonzaga, right? And so this is disconnected. Actually, each component would represent one of the dorms, and it'd be like one dorm would have a bunch of people clustered together, and then another, and then another. So this one here is not connected. And what would the degree represent in this case? My degree as a number is, can anyone describe in simple words what is, I mean, I'm not asking for a specific number answer here, but what would this mean? If I said my degree is 100, what does that represent in this graph? Still got an idea?
Like 100 people in like the dorm that you live in?
Yeah, it means that's how many people live in the same dorm as me. So my degree is actually, in this case, is equal to the number of people in my dorm. I suppose other than me. The number of other people in my dorm. Yeah, great. The number of other people in my dorm. So you could actually, figure out this degree if you really wanted to. Great. I heard another example was all Fairfield students, and there's an edge connecting them if they have the same hair color. I thought that was cute. That's a perfectly good example. Although I might say, like in real life, it's a little hard to tell if somebody has the same hair color as somebody else. Like, you have to be a little careful about what exactly you mean by the same. Just because hair shades are kind of on a spectrum, aren't they? But anyway, that sounded good to me. I heard one interesting example that I thought I would mention. How about the vertices, again, are all Fairfield U students? A lot of people went with this, maybe just because my examples were all like that. But of course, it doesn't have to be all Fairfield U students. And the edges connect. There's an edge, they said, an edge when the two students that I'm talking about have visited the same U.S. state. I liked this idea, although when I first gave kind of ambiguous feedback to these people, and I hope you don't mind me sharing my ambiguous feedback. When I first heard this idea, I thought, oh, that's a great idea. And then I thought a little bit more about it, and I thought, that's actually kind of a stupid idea. Not to say, I shouldn't have used the S word. This is a deceptively, it sounds interesting, but then maybe it's not so interesting, but for this reason, that makes it interesting. There's an edge when the two students have visited the same U.S. state. Anyone have a feel for what this graph looks like? Like, for example, if I just choose two students in this class at random, is there going to be an edge between them? Maybe. I think the answer is yes. Like, I happen to know for a fact that all of you here have visited the state of Connecticut. And so that means all of you here have an edge connecting you. I would say this graph, actually every vertex is connected to every other vertex by an edge, because every Fairfield U student has visited the state of Connecticut. Right? This is why I said this graph maybe sounds more interesting than it actually is on the surface. But this is something that can happen. So I would say we've all visited the state of Connecticut. I guess I'm not including. Don't we have like a nursing school in Arkansas or something like that? Somewhere else? Yeah, it's not Arkansas. It's some in Texas maybe. This is true. I'm not making this up. Do you know about that?
It's in Austin. Right?
In Austin, yeah, maybe. Yeah, it's true. So I'm not counting them. Sorry to them if they're watching on the YouTube. We've all visited the state of Connecticut, so we all have an edge to everybody else. So from that point of view, this graph is maybe not completely interesting. Like, it's just every single vertex has an edge to every other vertex. All right. There's actually a name for that. That's called a complete graph. All right. Great. Here's another example. So actually, nobody said this example, but I just want a little cautionary example. Here's a bad example. I've taught this class before, and this was a memorable example that I remember from a previous time. I asked some people to do this same example. They said the vertices are drinks at Starbucks. All right, I like this. So there's several different drinks that you can get at Starbucks, all right? Each one of the drinks is a vertex. And then they said there's an edge when it's coffee. Of course, not all the drinks at Starbucks are coffee, right? There's an edge when it's coffee. This, in my opinion, is a bad example. Anybody agree? It's not because I don't like Starbucks or whatever, but there's actually sort of like something is not really mathematically appropriate about this example. Anybody have feelings about this? I'm trying to caution against some problems if you're trying to make up examples like this. Maybe you all feel like this is a perfectly fine example. The idea is the vertices are the drinks at Starbucks. I'm totally fine with that. This is great. There's an edge when it's coffee. This is the problem. You can't really say that. When I say the vertices are drinks at Starbucks, so I have to imagine, okay, I'm thinking of two drinks, right? There's the pumpkin spice latte and the pink drink, all right? And I ask you, is there an edge between the pumpkin spice latte and the pink drink? And you say, oh, there's an edge when it's coffee. I would say, what are you talking about? Like, what do you mean by it? I mean, you should be talking about two things when you tell me, is there an edge from the pink drink to the pumpkin spice latte? To say there's an edge when it's coffee doesn't make any sense. So the problem here is this right here is supposed to represent a relationship between two drinks, right? These two drinks are the same color, or these two drinks have some ingredient in common, or something like that. These two drinks are both served at the same temperature. Like, you can say any of those would be great. When you just say it's coffee, that doesn't mean anything about comparing two drinks with one another. So I would say this right here, this doesn't describe a relationship between two drinks. That's what's necessary. When you tell me there's an edge from this one to this one, you have to somehow be describing two things and whether or not they are connected, all right? That's why this doesn't make any sense when it's coffee. Maybe you could say there's an edge between two drinks if they both have the same price, or if my mom likes both of them. Or it could be anything like that, but you have to somehow mention like both of them or one or the other of them. You can't just say this doesn't even make any sense. All right, this is my bad example. So just to caution you. Maybe we got 5 more minutes. I will give some like really real examples. So graphs come up all the time. Graphs are important. I just want to give you a few real life examples where you can imagine a graph and actually sort of think about important problems in those ways. So one important example in which we all use graphs all the time is road maps and navigation. If you look at a road map, you could think of the various streets as being edges in a graph, and in that interpretation, each vertices are, I would say, road intersections, and the edges are roads, right? So the graph, the graph would look something like this kind of a thing. If you're in a city, the graphs, the roads are usually like in a very regular grid-like pattern. In the town of Fairfield, the roads tend to be sort of swervy, curvy, but that's all right. It would look something like this. The vertices are intersections of roads, and the edges are the roads themselves. And of course, this is super important. And actually, when like your GPS lady is giving you directions, what is she really doing? She is finding a path in the graph to get from one place, like your current location, to some other place, right? So I would just say finding paths is super important. This is exactly how, there are tons of mathematicians who just study graphs all the time. And there are super important mathematical questions related to finding good paths in graphs. And they are used by these navigation, algorithms. So this is extremely important. How about another important example? Computer networks. These days, pretty much every computer, or all the computers that you interact with regularly, are connected to other computers by the internet, either by wired connections, or more likely some sort of wireless connections. There's Wi-Fi networks or cell phone networks. So in this case, the vertices are individual computers, and of course I'm including things like cell phones and everything is a computer these days. Your iPad and also an ordinary desktop or laptop computer. The vertices are computers, and then the edges would represent network connections. And these can be by wires, or more likely by wireless connections. Like your phone is connected to a tower somewhere wirelessly, but then that tower actually has big wires connecting it into the rest of the internet. So edges are network connections. These can be wired or wireless. And also, it is super important to find paths here. So finding paths is necessary, and I will say is actually kind of big business. Like, for instance, if I want to send a text to my wife, like right now, from my phone here, my text would be sent by a wireless connection to the, probably to some Wi-Fi, like my phone is connected to a Wi-Fi in this building. And then along real physical wires, it would travel somewhere else to a cell phone tower, and then from the cell phone tower, it would go wirelessly into my wife's phone. Now, every time that happens, your phone or somebody has to actually find a route through all of those connections to get to my wife's phone, right? So you have to find a path. Anytime you do anything on the internet, there has to be a path that is located in this giant sort of mess of connections. Like, everything is connected to everything else. And this is big business. So there's actually individual big computers and even small computers to do this, where their only job is to figure out, if I want to send a text to my wife, exactly which connections does that text have to go through in order to get to my wife. And this is called, there's sort of special devices to do this. And these are things probably you have all heard of. Paths. Special devices to find paths, they are called routers, right? Because their entire purpose is just to find an appropriate route to get from my phone to my wife's phone through the various connections. All right, and sometimes you can go just straight across. Like if you use AirDrop on an iPhone, that's just a direct connection, you to somebody else. But most everything else you do goes through some, maybe hundreds of other connections before you actually arrive at your destination. All right, one last thing. I know it's time to go. I'll just say it out loud. Social networks are the same way. You can analyze something like Instagram as every user is a vertex, and there's a connection between you and somebody else if you are friends on the social network. And again, you can think about all those things in terms of graphs. All right, we'll get to more specific questions next time.